Okay, so this is lecture number 19 on refraction. So I'm going to record these lectures in real time from here on out. Just too time consuming to do them separate. So first off, what is the phenomenon that we're looking at? If I use this laser pointer to shine a laser through this piece of glass, you can see it's going straight through, right? Now as I start to bend the angle of incidence into the glass, you can see that it does actually bend compared to what the angle of incidence is. So you can probably see that. Now the bending is not all that extreme, but it's clear that here I am near, probably 70 degrees, 60 to 70 degrees, right? And we have refraction in there. The beam is bending much less than the angle of incidence here. So this phenomenon that light is bending inside of a material is the phenomenon of refraction. That's what we're going to explore today. So the first empirical observations of this were made by Claudius Ptolemy in about 140 AD. Right, this will be a similar time to Heron of Alexandria, who gave us our law of reflection. And here's his data. So he observed light bending through the surface of water. And I guess I should probably stand over here. And he actually took measurements of this, and so he noticed that if he had an angle of incidence of 10 degrees, then the angle of refraction inside the water was 8 degrees. At 20 degrees, 15.5 degrees. At 30 degrees, 22.5 degrees. Let's just jump ahead here. At 60 degrees, 40.5 degrees. So what does that look like? So this is my normal, and this is where the water is, and this of course would be air. If we came in with an angle of incidence of 60 degrees, if this is 45, then the 60 is going to be like this roughly, okay? So there's the 60 degree angle, and he observed that the light refracted at 40.5 degrees. So again, this would be 45, so 40.5 is going to be over here. So we see that it's bending towards the normal. And of course, he wanted to know what is the relationship between the angle of incidence and the angle of refraction. Remember that from before, the angle of incidence and the angle of reflection are one and the same, and we demonstrated this using Heron of Alexandria's principle of least distance, right? Now, will least distance work on this? Well, if we imagine a point A right here and a point B over here, right? We know what the shortest distance from point A to point B is, right? The shortest path is a straight line. It's this path right here. So why should light take this other path? That's the question. So obviously least distance is not going to be a principle that holds for refraction. Okay? And furthermore, if the principle of least distance is not correct, then how do we rectify our understanding of reflections, given that we came up with this principle of this law of reflection using this principle of least distance? So to answer that question, let me give you an alternative problem. Imagine that point A is a lifeguard tower, right? And point B is a drowning swimmer, right? This comes right out of Feynman's lectures on physics. So here's the lifeguard, here's the drowning swimmer. The lifeguard has to make the decision, how do I get to the swimmer in the quickest possible time, okay? Now, as is common with all peoples, we can travel much faster on land than we can in the water, right? When we swim in the water, it's slower. So to take this direct path from A to B, right, you can see right here, we've got a pretty long swimming path. How much longer is it than, say, this path shown by the light refraction that we talked about earlier, right? Well, if we construct a perpendicular to this right here, right, this is the extra distance, right, that we travel by going straight into the water, by running straight towards the drowning swimmer. Do you see that difference? So we're spending more time on the land, right? If this is the actual path that the lifeguard decided to take, it would mean he spent more time on the land and less time in the water, right? Now he could have, taken a route, to minimize the time that he's in the water completely, could have been like a path going from A to here and then into the water and swimming. Then he'd be on land for a long, but you have to run on land for a longer period of time. So there's some compromise, and it depends on how fast you can swim versus how fast you can run. And if it turns out that your swimming speed is obviously your swimming speed would be slower than your running speed, right? And if the factor by which it's slower is by dividing, whoops, sorry, I put it on the wrong side. If my swimming speed is my running speed divided by 1.33, right, then it turns out that this figure that I've drawn here would be the quickest path to get to the drowning swimmer, okay? I'm not going to prove that for you here, I'm just going to point that out. That if we were to happen to perform all these experiments with running to different points on the beach before we get into the water and swim straight to the swimmer, right, we would find that if this was the optimal path, that means that our running speed, or our swimming speed, was our running speed divided by 1.33, okay? And we'll come back to that in a minute. So why would you bend from going straight through from A to B directly in a straight line? Why would you take this alternative path with these bent rays? Well, if light traveled at different speeds in different material, then that would be one reason to, okay? And as it turns out, it does. Light has a speed, and we're not going to get into the details of it. Typically, we write the speed of light, and we call it c. It's about 186,000 miles per second, or 3 times 10 to the 8 meters per second, okay? Or it's roughly 1 billion feet per nanosecond, I think is another useful metric for the speed of light. But it has some finite speed, yeah?
1 foot per nanosecond.
Yeah, well, exactly. 1 foot per nanosecond. What did I say?
You said 1 billion feet per nanosecond.
Oh, I don't know why I said that. Yeah, I think it's 1 foot per nanosecond, roughly, is the speed of light. So, where was I? It's the speed of light. So it has some speed. But, and we'll learn, right, that the famous experiment that demonstrates that the speed of light is constant, right, in all frames of reference. And we'll get to that later. But I just want to point out that the difference here when we say that the speed of light is slower in some materials, right, there's a reason for this. And it's not violating Einstein's observation that the speed of light is a constant in all frames of reference. That's not what it's doing. It has to do with the way that light interacts with materials, okay? So the speed of light in vacuum is 1. The speed of light in air is about 1. It's like 1.000 c divided by 1.00079, I think. So it's very nearly the same as the speed of light in vacuum, okay? And so, but we can use a nice reference. We'll call it the index of refraction, right? And it's a number that if we want to say the speed of light in, say, H2O, well, let's write it like this. Where's my eraser? Well, I want to write that the speed of light, that's not what I want to write either. The speed of light in H2O is equal to C divided by N sub H2O, which is equal to C over 1.33. Okay? So this N is called the index of refraction, and we'll see that it relates to this angle of refraction here towards the end of the lecture. But this is how we write that the speed of light in water is actually slower than the speed of light in air, and you can characterize that by this index rather than actually giving a number, okay? Because we don't want to have to divide 186,000 by 1.33 and have some number that we cite instead. So we can just say this is the factor by which it's slower, okay? So if n equals 1, the speed of light in a material that has an index of refraction of 1 would be the same as that in vacuum, right, in space. Okay? You understand?
Yes.
So different materials have different indices of refraction, which means that the bigger the index of refraction, the slower light travels through that material. So in water, it's 1.33. In glass, it's about 1.52. In diamond, it's, I think, 2.52. So even slower in diamond. Yeah. So perhaps a possible explanation is that just like with the beach problem, right? Why did he choose this strange path going from here to, I'm going to call this point P, just so we have a reference for it. Why did he travel from A to P and then to B instead of going straight from A to B? Well, because he ran faster on the land, right? and his speed in the water was 1 point, it was 1 point, you know, the speed in land divided by 1.33. It's probably a better way to say that. And so that's why he took this path, okay? Because it got him to the swimmer in the least amount of time. And so now we get the kind of the big idea. So maybe it's not a principle of least distance, right? So much as it is a principle of least time. Now this won't affect our reflection laws at all, right? Because if we have two paths on a reflection, right? Here's my normal, here's the surface, right? Here's point A, here's point B. This distance, which we called before, right? What is distance? Well, it's speed times time, right? So this is the speed c times the time it took to travel here. And this over here, we'll call this t1, and this will be c, t2, right? Well, notice the common factor of c in there, right? Because the speed of light is the same on both arms, because this is taking place in air, right? So really, instead of least distance, it turns out to be a principle of least time, okay? Does that make sense?
Yes.
So that's what we're going to consider now. And so I'm not going to draw a bunch of pictures and make a bunch of measurements. Instead, what I did is wrote a computer simulation to try every possible angle. So I defined a point A and I defined a point B, okay? And I said find the path for light to get from A to B if the index of refraction in this starting material is air, it's a 1, and this material here is whatever I've set up here. So in this first example, if they're both in air, right? So if this is air and this is air, right? Well, I don't know. That would be misleading to erase that. If my two materials are air, right, I would expect this dotted line, this straight path through, right?
Yes. And
so given where I put A and B, it turned out that came out to be 45 degrees, okay?
Okay.
This is A, this is B. And so you can see that it does travel the straight line path going from A to B. Okay? So that's it. Both of them have an index of refraction of 1. So the speed in this material is the same as the speed in this material. Okay? And this is all the different angles of incidence that it considered, right? And this is the time. It's not really in seconds. It's a typo there. But this is a measure of the time that it took to get there, right? So one thing you'll notice is it's rather broad here at the bottom, right? Wherever the minimum time is, right? It's quite flat in that region. It's not a sharp minimum, okay? So this is for water. But let's look at... Oh, that was for air. This is for water, okay? So now that we've set the index of refraction to be 1.33, that is the observed speed of light in water, okay? We would divide the speed of light in vacuum by 1.33, and that would give us the speed in water, okay? What do we find then? Well, now the angles, it's clearly bent, right? Just like our laser pointer at the beginning, yeah?
Yeah.
So the light comes in, instead of taking a straight path across, it's going to travel a little more in air and then bend in, you see? And so the angle of incidence that it found, the minimum for it anyways, turned out to be somewhere around 60 degrees. Oh, here it is, 59 degrees. And the angle of refraction was 40 degrees. So if we look at the table over here that Claudius Ptolemy constructed, when we find, well, we have 60 degrees, which is pretty close to 59 degrees, and he found a 40.5 degree refraction angle, whereas our simulation found a 40 degree refraction angle. Okay, so that's pretty close. Pretty good agreement, I would say, right? Again, notice that where the minimum takes place, right, for this minimum angle of incidence here, it's pretty flat in that region, right? That's going to give us some insight into how to show what this new law of refraction is. Here we have glass. That would be similar to what we did at the beginning of the lecture with the laser pointer, right? So if we have glass as our material instead of water, the index is higher, 1.52. That means that light travels slower in glass than it does in water, okay? And so in that case, we found the optimal angle of incidence to be 64 degrees and the angle of refraction to be 36 degrees. So you can see it bent more towards the normal than it did with water, okay? And in general, that's a trend we're going to see. The higher the index of refraction, the slower light travels in that material, the more the light bends towards the normal, right? Do you understand what I mean by bends toward the normal? This is the normal. Bending towards the normal is like this, you see? Understand?
I think so, yes.
Okay. And then finally, what does it look like for diamond? Here's diamond. Here we get actually the sharpest of the peaks, right? This is not generally all that flat down here, right? It's more peak-like than the previous graphs have been. And you can see the angle is it's bent in quite a bit. So it spent a lot of time traveling in the air because it travels so much slower in the diamond, right? So it's going to spend more time traveling in the air to get to the point B as quickly as possible. Let me go back to the previous graph. Glass, and let's look at water. Yeah. So what I want you to observe, right, is that where the minimum is really, it's quite a flat region. And so what does that mean for us in terms of what can we learn, or how can we figure out what this law of refraction should be? And so I'm going to reproduce the drawing I made in my notebook here as best I can. So let's first assume that we found ourselves the actual path, right? And then we'll say that this is the surface that we're going to interact with. Here is a normal to that. And then we'll have this bend just a little bit here, like so. And so we'll say that this is A. Or actually, I'm going to call this alpha. Alpha, I'm going to call this point beta. And I want to consider another path that's nearby. Because according to this, if I select a nearby path, the travel time, shouldn't change very much, right? That's what being flat down here kind of means to us. So if I find the minimum, 59 degrees, if I tried any other path nearby that, the travel time should be just about the same, right? You understand?
Yes.
That's what this is telling us. It says if I chose 60 degrees instead of 59 degrees, the time it would take to get there is about the same, right? So we're going to rely on that, and I'm going to draw another path, which I'll exaggerate just a little bit here. I have enough ruler to make that just barely. Okay, and that of course means that here will be the path down to this point. Okay, and I need to label the points on here. I'm going to call this point here A. Actually, I should call it uppercase A. We always in geometry label things uppercase. And I'm going to call this point B. Okay? And now I'm going to construct a right triangle by drawing a perpendicular line. It goes from A to this new point, which we'll call, I'm going to call it D. And similarly, I'm going to do the same thing here. Drawing a perpendicular, so this is a 90-degree angle, this is a 90-degree angle, and I'm going to call this point C. Okay? And you'll notice that the difference in the paths, right, in the first path that gets us there in the shortest time, and this alternative nearby path, right, the difference in that is, in the first leg of the trip, the difference is that it took dB, right? We traveled dB longer than we did on the original path, okay? But we saved, in doing this, right, we saved AC, right, traveling in the second material. Okay, so call this 1, call this material 2. You see that? So I traveled a little bit more in material 1, right, by a distance of dB. Okay, and if I write that as the speed of light times time, then this, you think of this as a time, right? But I saved this travel right here, right? I didn't have to go AC, right? So I'm assuming these angles are rather small, so that this and this are roughly the same length, right? And so that's what I saved. And so what can I write down with that, right? I can write down that if these paths are nearby, then it should be the case that the line dB, right, is equal to n, that's that index of refraction, right, times AC. Okay? So I have to multiply by n so that I account for the slower travel time in the material, number 2. So this distance dB should be equal to this distance AC. Okay? That make sense? We good so far? Now, but I can recognize through trigonometry, if I call this angle theta 1, okay, and what about, yeah, this angle will be theta 2. Notice they are not the same because this line and this line are not parallel, right? So don't make the mistake of thinking that theta 1 and theta 2 are the same. They're actually different, okay? Even though they look like alternate interior angles, they're not. At least I don't think. No, they're not. So I can use a little trigonometry, right? AB is the common hypotenuse to these two triangles, the triangle with angle theta 1 and the triangle with angle theta 2, right? So this I can write as AB, that's the hypotenuse, times the sine of theta 1, okay? The opposite, right, is this side dB, see? So dB divided by the hypotenuse, that's what the sine of theta 1 is, right, times AB will just give me dB back, right? This should be equal to n times, well, AC is this leg here. That's the opposite to theta 2. So I can take AB again times the sine of theta 2. Divide both sides by the common hypotenuse, and I get that the sine of theta 1 is equal to n times the sine of theta 2. Now, of course, I really would have liked to have used this complementary angle to theta 1, right, which we would call the angle of incidence. However, it'd make it harder to read. I think it's easier to see it this way, using these sections that are next to each other like this instead of these sections, which are the same value, but a little bit different. But the result is that I can now extend this, right? With this n is really the ratio of the indices of refraction for these two materials. Air is 1, so you can really think of this as the index of the second material, okay? But we can use this to write what's known as Snell's law, okay? So Snell figured out this relationship in Ptolemy's table here, which this is 140 AD. Snell was around 1620, I think. And around the same time, Fermat, the mathematician, had proved this using this principle of least time, which is kind of what we did here. Technically, to do this principle of least time, you need some calculus, and so I did not do the usual demonstration for it, okay? But this, I think, is just fine. Actually, it has more insight, I think. This is also from Feynman. This is his argument. And so what is Snell's law in the end? It says that N1 times the sine of theta I, we call that the angle of incidence, is equal to N2, the second material, times the sine of the angle of refraction. Okay? And so if we use that law now, right, this is the correspondence using Snell's law for a 10-degree angle of incidence, right? We should find in water, which has an index of 1.33, a 7.5-degree angle of refraction, comparing that with the experimental results of 8. So there was some error in the experimental results, probably also some interpolation here, but that's beside the point. But in general, you see they agree pretty well, right? And similarly, in the computer simulations that I did, you can see over here, did I print the error out? No, I didn't. The error is very small in the computer simulation, but this is the angle we should have got, 40 degrees, and that's what we found, right, for that particular case, for water. For glass, we should have found 36.3. I think we did find somewhere close to 36.3, but I just wrote down 36 in the output. And then for diamond, Snell's law tells us that for a 73-degree angle of incidence, we should get a 23.3-degree angle of refraction, which is what our computer simulation found. All right, so we're working a problem here where we're going to consider light incident on a material with an index of refraction of 2, and we're going to ask what's the angle of refraction, given that the angle of incidence is 45 degrees. So how would we solve this, right? Well, air, n equals 1, right? N equals 1 in air. In this mystery material, we're saying the index of refraction is 2, so n will be equal to 2. So how do we solve this equation to find the angle of refraction? Well, we can divide both sides by n2, right? That's going to give me that the sine of the refractive angle is equal to 1, well, I'll write it out, n1 over n2, times the sine theta I, angle of incidence, right? Now I can plug in some numbers to this, right? n1 is 1, n2 is 2. The sine of 45 degrees, who remembers the sine of 45 degrees?
Square root of 2 over 2.
Square root of 2 over 2. So this will give me the square root of 2 over 2, which you can also, you guys remember that this is the same thing as 1 over the square root of 2? Because if I multiply the top and bottom by the square root of 2, right, this will cancel. Oh, no, I'm sorry, I didn't want to cancel, that was dumb. Square root of 2 times square root of 2, right, is, let me just do this as an aside. square root of 2 over 2 times the square root of 2 over the square root of 2 is equal to, square root of 2 times square root of 2 is 2, right? Over 2 times the square root of 2. The 2 is canceled, and I'm left with 1 over the square root of 2. Okay? So I can write this as 1 over the square root of 1 over 2 times the square root of 2 because I have that 1 over 2 factor there in there, right? So that's what this is equal to, and we would then have to guess what angle has a sine of 1 over the square 1 over 2 times the square root of 2. Actually, maybe I should have left it the other way around, huh? Well, then it would be over 4. It's not gonna help. So how do we do this? We can get our calculator out, right? And what we want to do, we write theta r is equal to the inverse sine of 1 over 2 square root of 2. Okay? So for these Snell's law problems, you have to punch things into the calculator rather than rely on your knowledge of some basic angles like 30, 60, and 45. So where is the inverse sine key? It's right above the sine key on the TI-84. So I hit inverse sine, and 1 divided by 2 times the square root of 2. And that tells me that it's 20.7 degrees. I have it set to degree mode, so I'll get an answer in degrees. And so this is equal to 20.7 degrees. Okay? So that's how you do these kind of Snell's law problems. You're going to have to get out the calculator and use the inverse sine, also called the arc sine button. Okay, any questions? Okay, no questions? All right, that's the end of the lecture then.